Alright, so in our previous chapters, we went through parts of an atom. We talked about the periodic table and the organization. We've talked about metals and non-metals. And then we talked about specifically electrons and electrons, how they were organized. So we are now going to start talking about how elements on the table combine with one another to form ionic and covalent compounds. And so in this chapter, we're going to be focusing on specifically ionic compounds. So before we can do that, we need to review valence electrons. So if you remember, atoms have a full set of electrons that is equal to the number of protons, but they were organized into these levels, 1s2, 2s2, 2p6, etc. And the valence electrons were just the ones in the outermost level, and they are going to be the ones we're going to focus on for the rest of the year because they're the ones that are involved in bonding, giving elements their chemical properties. So in the old 1A through 8A system, which I'll show you in a second, the group number indicated the valence electrons. And again, this would be the highest in level, the outermost shell only. So it usually would only be S and P, not D or F block. Electron dot structures were a way of representing just those valence electrons. So before we draw the dots on these, let's go to the periodic table really quick. And just a quick reminder, in other words, if we wrote the electron configuration, let's just say for magnesium, so let me just get my pencil here, and if I wrote it for magnesium, here it would be 1s2, 2s2, 2p6, 3s2. The valence electrons would just be the outermost level, level 3, and there would be 2 valence electrons. Now in the older system, you see here 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A, that number above the column would indicate how many valence electrons. So everything in this first column has 1. These all have 2. We're going to skip these. 3, 4, 5, 6, 7, 8. Except for helium. Helium actually only has 2 valence electrons because it only has 2 total electrons. And if you remember, the outer shell, remember there was only S. So 2 electrons filled it. I don't know if you remember that. Anyway, but everything else in that column has 8. So you could pick any element of these representative elements like, oh, germanium. How many valence electrons does it have? Oh, it's in column 4A. It has 4. Now, in the newer system, it's just numbered 1 to 18, and that's why we had you guys, when you made your periodic tables, write the 1 through 8 there as a reminder of how many valence electrons there were. Now, I'm not going to spend a bunch of time doing the dot structures. I'll do a quick reminder. So now that you know how many valence electrons, you could look up the element, and then you would draw in the dots. So for chlorine, it actually has 7, so it would be 1, 2, 3, 4, 5, 6, 7. Potassium only has 1. Oxygen has 6, so you would go 1, 2, 3, 4, sorry, this board does not like me drawing dots, 5, 6. You have to draw them by themselves first. Like if you were going to do carbon, which has 4, you would do this, 1, 2, 3, 4. You would not do 1, 2, 3, 4. We're kind of representing that they don't want to be next to each other. So that's why this number 5 and 6 are by themselves. They don't have to be in those locations. Like you could also do 1, 2, 3, 1, 2, 3, 4, and then you could do the 5 and the 6. Nitrogen has 5, so we're going to do 1, 2, 3, 4, 5. Magnesium has 2. We're going to do 1, 2. Technically, you could also do 1, 2. Again, the board doesn't let me draw dots very well. All right, so moving on. So that's our periodic table. So then there was a rule called the octet rule that said that atoms would either gain, lose, or share electrons in order to get 8 in their outer shell. And they're going to do whatever's the easiest thing to do because these things require energy. And if they have a full set of 8, then that's like your noble gases, they're not going to react. Now, hydrogen and helium were exceptions to this because they're so small, they only have 1 level. So 2 would be a full outer shell for hydrogen and helium. Helium has a full outer shell. Hydrogen typically loses 1 and forms a hydrogen plus 1 ion. All right, so moving on. So ions. So positive ions are elements where they have lost electrons. They're also called cations. And this is going to be group 1, 2, and 3 are always going to form positive ions. Technically, so is your D block. They are metals also. Remember, the charge is going to be positive because electrons themselves are negative. And then when we name our positive ions, the name is just going to be the name of the element with the word ion after it. So I'm actually going to skip this bottom section and just show you some examples. So skip that for now, and let's take a look. So group 1A, they all have one valence electron. The easiest thing for them to do is to lose that electron. So like, for example, sodium is number 11. So here's our nucleus. So sodium has 2 in its first shell. Then it has 8. 1, 2, 3, 4, 5, 6, 7, 8. That shell's full. And then its last shell has just 1. It ends with 3s1. And that's the 11 electrons. So remember, one valence electron, right? So what's going to be easier to have a full shell? Would it be to gain 7 or lose the 1? And if it loses the 1, that outer shell would just disappear, right? So it's going to be much easier to lose 1. It's almost impossible to gain 7. And so that's why sodium and all the other ones in this column will form a +1 ion. Notice they wrote 1+, but usually if it's just a +1 charge, you actually don't write the number 1. You would just write plus. All right, group 2A, same situation. They have 2. They either have to gain 6 or lose 2. They're going to lose 2. So look, beryllium ion, magnesium ion, etc. All right, group 3, same thing. It's going to be easier to lose 3 than to gain 5 in order to get 8. So here's some examples: boron ion, aluminum ion, gallium ion. All right, and group 4 is kind of unusual. Group 4, it's actually hard to gain or lose more than 3. So they actually tend to share electrons, group 4. And group 8 usually doesn't form ions either, because that's your noble gases. They already have a full outer shell. So 4 and 8, although there are some exceptions, these are usually not going to form ions. All right, now let's go back and talk about negative ions. All right, so for negative ions, we're going to change the ending to "ide." So these are going to be non-metals, and they're going to be on the right side of the periodic table. So for example, chlorine becomes chloride, sulfur becomes sulfide, oxygen would become oxide. So now, people were getting thrown off in class by this one. So if you notice here, these are going to form a -3 charge. So let me rewrite what we've been doing here. So remember, the number of valence electrons was 1, 2, 3, 4, 5, 6, 7, 8, right? So these form a +1, these form a +2, and these formed a +3. These don't tend to form charges, although we're going to talk in a minute about how tin and lead do, but these usually tend to share more likely. Then this is not going to be a +5. This is going to be a -3. Why? Because it wants 8, right? Remember? So if it's got 5 in its outer shell, 1, 2, 3, 4, 5, its options are either to lose 5 and get a +5, or gain 3 and get a -3 charge, and that's going to give it 8. So these are going to, the easier thing is going to be to gain 3. So remember, negative charge because it has 3 extra electrons, which are negative. So -3, -2, -1. So +1, +2, +3, -3, -2, -1. So this is going to be nitride, phosphide, arsenide. Let's look at our next group, 6A. So these, remember, this is going to be 3, 4, 5, 6, 7, 8. These gain 2, so a -2 charge, because they need 2 more electrons. 2 electrons, which are negative: oxide, sulfide, selenide. These are just some examples. Group 7A, these have 7. They need 1 more, so they're going to get a -1 charge. So fluoride, chloride, bromide, iodide, etc. And then group 8, these are our noble gases, so they're not going to form ions. All right, now transition metals. They are metals, but they are not always going to get the same charge. So unlike the previous ones where it always forms a +1 or it always forms a -2, that's not going to be the case for transition metals or D block elements. And what will happen with them is they will get what's called a pseudo noble gas configuration. So for example, zinc, which is located here. So if we look at our periodic table, right? Zinc is right here. So zinc would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. So it ends with 4s2, 3d10. Now here's the thing. What is it going to lose? It's actually going to lose 4s2, 2 valence electrons. So it would have almost the exact same electron configuration as the noble gas before it, except it has the D, the 10D here, the 3d10. So they call it a pseudo noble gas configuration because it's just like the noble gas, but it also has D block. So these are in the old way of doing this, these were called the group B elements. These have more than one possible charge. So for example, iron can form iron 2 or iron 3. And the reason, what we'll do is we'll use a Roman numeral to indicate which one it is. Alright, so if we look at the transition metals, so because they can form more than one ion, we have to have a special system for naming those. So I can't just say iron ion, because you wouldn't know what the charge was since it can form multiple charges. So we use what's called the stock system, and the stock system is going to use a Roman numeral to tell you what the charge was on the ion. So for example, Cu, copper, with a +1 charge is copper 1 ion. Cu + 2 is a copper 2 ion. So again, this only applies to D block, but you wouldn't write calcium 2 ion, because calcium always forms a +2 charge. Now there is an older system called the classic system, and it uses suffixes instead. You don't have to know this for the test. So the classic system, it would have, for example, copper with a +1 would be called cuprous ion. This ending would always be the smaller charge. And then ic is for the higher charge. So cupric ion and cuprous ion. But this one will be on the test. The newer way of doing it is with the Roman numeral, which tells you exactly what the charge is on there. Now there's also a couple of exceptions. These are transition elements. So they are in D block, but because they always form the same charge, you don't use Roman numerals. So you don't call this silver 1 ion, it's just silver ion. And another exception, tin and lead. So tin and lead are not in D block, they're actually in P block, but because they can have more than one possible charge, they do get a Roman numeral. So here's the exceptions we just talked about. So tin and lead, technically these are the ones that should get Roman numerals here in D block. Tin and lead are not in D block, but they can form multiple charges, so they do always get a Roman numeral. So you have to memorize that. And then these are the ones in D block that don't get a Roman numeral. Zinc, cadmium, and silver. These three. This always forms a +1. These always form a +2. So you do not include, so you wouldn't say silver 1 ion, you just say silver ion. Alright. I think this is just showing, these are those exceptions I just mentioned. Silver, zinc, cadmium. Alright.